Hello, everybody. There was a question today towards the end of the class about example 5 of section 3.9, related rates, page 248. So let's look at it, look at it now. A man walks along straight path. So straight path, walking along, let's call that X. And actually, there's a really nice picture that goes with it. At 4 feet per second, what does that mean? That means that dx dt equals to 4 feet per second. No. And there is a searchlight somewhere down below in here. There's a searchlight. Okay, and the man is starting to walk from here, then goes to here, and just keeps walking. And notice that this theta, the angle, this angle is gonna get wider and wider and wider. So the theta is going that way, is getting wider. And this distance right here, according to problem, is 20 feet. And what else we know? At what rate is the searchlight rotating? Okay, so since we are talking about the rotation, we are talking about the angle, if we call this theta, like the picture. So we are looking for d theta dt. At what point, when the man is 15 feet from the point on the path closest to the searchlight? Well, this straight line right here is the closest to the searchlight. So what we want is find d theta dt when x equals to 15 feet. Okay. So what's happening when x equals to 15 feet? When x equals to 15 feet, so this is 20. Let me change my picture a little bit. I want to make this actually a little bit. If this is 20, make this 15 so it's more consistent. So this is 20 feet, this is 15 feet, and here's my theta. This is one of the right triangles that we encounter very often. If you have one side 15, one 20, the other one must be 25. Or you could use just a squared plus b squared equals c squared. So once again, we want to find at that moment, we do want to find out when x is, when x equals to 15, what is d theta dt. Now I need a relation between the theta and my x, because my x will keep changing. I know that theta, based on math 142, based on the trick that we learned, let's use tangent of theta. So we know that tangent of theta equals the side opposite, which is x, because remember he keeps moving, x is changing, divided by the adjacent. The 20 is not changing. This 20 feet is fixed. And I don't know about you, it's easier for me to look at this as tangent of theta equals 1/20th of x for the purpose of taking the derivative. What is derivative of left-hand side in relation with time? I get secant squared of theta d theta dt equals 1/20th dx dt. And now I have to divide both sides by secant squared of theta. I don't like that, so I'm going to rewrite the secant squared. Instead of secant squared, I'm going to write 1 over cosine squared. I'm going to write 1 over cosine squared of theta d theta dt equals to 1 over 20 dx dt. And now I'm going to multiply both sides of this equation by cosine squared of theta. So I'll end up having d theta dt equals to 1 over 20th cosine squared of theta. And dx dt was given to us as 4 feet per second. So I'm going to put times 4. Okay. So what can I do in here? I can do one baby simplifying and say that d theta dt equals to 4 cancels out with 20, 1/5 cosine squared of theta. But what is cosine of theta at that moment? So when x is 15, when this is 15, and this side was 20, and we say this was 25, cosine of theta at that precise moment is adjacent over hypotenuse. So d theta dt equals to 1/5 20 over 25 to the second power. Okay. And now I have to simplify this. This gives me 1/5. In the parentheses, I have 4/5 to the second power. So this gives me 4 squared is going to be 16. Let me change color. Divided by 5 squared is 25 times 5 is 125. And that's our answer, radian per second. I hope you enjoyed this video and thank you